Hello and welcome to the Postcard Professor, where we take complex ideas and explain them in the space of a postcard. In this video, we will be building a relatively simple simulation in ANSYS. Now, in order to create a simulation, we need 5 things. First off, we need the geometry. In other words, what is the shape of the object that we want to simulate? We also need a material. What is that object made out of? We need loads. What is pushing or pulling on the object? We also need constraints, which just means how are we actually holding that object to keep it from moving? And then finally, we need a mesh. So this answers how the program actually understands what the shape of the object is. All right, for our geometry, we're going to look at a pretty common problem, but this is just going to be a flat plate that has a hole cut out of it. And we're going to need to be able to dimension this, right? Everything needs to be known about this object. So the length of this thing is going to be 5 inches, and the height is going to be 2 inches. The size of this hole is going to be 1 inch in diameter, and then the entire thing is going to be just 1/10 of an inch thick. So that is everything we need to define the geometry. Now for the material, we don't care that much about what it is, so we're just going to leave it as the default. And for ANSYS, the default is structural steel. For the loads and constraints, our goal here is going to be to put this thing in tension, to pull it on both sides, and we're going to have 1,000 pounds of tension. So to do that, we're going to pull on the right side with a total force of 1,000 pounds. So that's going to look like a distributed load on this face. And then for the constraints, we're just going to hold it on the left side here. So the type of constraint is a fixed support. Basically, it just means that this left side is not going to be able to move. Then for the mesh, again, we'll talk about this more later, but for starting, we're just going to use the default ANSYS mesh. And then in later videos, we'll take a deep dive and figure out exactly what that mesh does. All right, so these are all the inputs into ANSYS, but we also need to tell ANSYS what we want out. And there are a lot of options here, but typically we're going to be interested in the deformation of the object. We're going to be interested in the stress at different parts of the object, and we'll be interested in the safety factor. And if you don't know what these mean, we'll get to that whenever we see it in ANSYS. So that's enough for now. Let's go ahead and go to Autodesk Inventor and make this object. Okay, overall, this isn't too bad. We're going to start off with a rectangle, and I personally prefer making things symmetric about the origin if I can, so I'm going to use the center point rectangle here. Now, once we have that, we need to dimension the sides. So one side is going to be 5 inches, and the other side is going to be 2. Now, since we used the center point rectangle, it's going to be really easy to put a circle right in the middle for the hole. And we need to set the diameter of that to 1 inch. Then to get the thickness, we're going to extrude everything but the hole by 0.1 inches. And once again, I'm going to do that symmetric just so that everything is symmetric about the origin. Finally, we're going to save it and name it something that we can find later. All right, before we switch over to ANSYS, let's make sure that the connection between ANSYS Workbench and Autodesk Inventor is enabled. To do this, we go to Tools and then Add-ins. We're going to scroll all the way down to the bottom and we're going to look for Workbench. And the boxes should be checked just as you see here. Not blocked, currently loaded, and set to load automatically. Once that's done, we are good to switch over to ANSYS Workbench. All right, now that ANSYS is loaded up, the type of analysis we want to perform is called static structural. So that means that our solution doesn't have anything moving around, and we are just looking for applying some forces, getting out the deformation and stresses on that object. So the first thing we do once we have the static structural model in the workspace is import our geometry. So we right-click on this geometry section, and then we choose import geometry. Now, if the part we just made doesn't show up right away, you might have to browse for it instead. Once you have found that part file, we can double-click on Model in order to open up ANSYS Mechanical. Once Mechanical opens, we should see our geometry right away. If you didn't, you may need to go back and look at the add-ins in Autodesk Inventor. Now, if you remember from our initial discussion, there are 5 things that we're interested in tackling here, and 3 of them are listed in the model outline over here to the side. You see the geometry, the materials, and the mesh. We've already taken care of the geometry, and the material will be set by default to structural steel, and the mesh is showing a little lightning bolt, meaning that it still needs to be generated. We'll leave that be, and it'll generate automatically with the default mesh whenever we solve. So let's add the other 2 pieces. First, we'll add a constraint called a fixed support, and we do that by right-clicking on static structural in the project outline, then hovering over insert, then finding fixed support in the menu. And if we look down here at the fixed support details in the little details tab, we see that geometry is highlighted. We are going to select the face on the negative X side over here. In order to rotate my field of view, I'm clicking the middle mouse button, then dragging. You can also go up to this row of small buttons at the top and click the rotate button, and then that allows you to rotate around using left click instead. All right, to select the surface, since we clicked the rotate button, we have to go back to the Smart Select button. That's normally chosen by default. We could also click this face button, which only allows us to select faces. Either way, we'll select the face that we want for fixed support, and then go back over to the Details tab and click Apply. Now that that's done, we can add a force by right-clicking again on Static Structural, hovering over Insert, and then this time we're going to choose Force. Once again, we select the face we want, and then click Apply in the Details tab. Now, for this one, it needs a little bit more information. We also have to choose the magnitude of the force. And you can tell that you still need to do something. One, because there's a question mark next to the force in the project outline. And then also down in details, this line is highlighted. If you're in dark mode like I am, this will be highlighted orange. And then in light mode, I think it's blue. In any case, let's go ahead and set the force here to 1,000 pounds. I'm currently in metric units, so if I just type in 1,000, it's going to put it into newtons. And so if I want pounds here, I either need to convert the force manually on my own, or I can switch ANSYS's units to US units. So I'm going to click down over here on the units, and then choose the US customary. And then once I put in the force, you can see the vector pointing out of that surface we chose. And that's going in the direction we want, so we're good to go. And I'm going to go ahead and switch back to metric just because I'm more used to those units. Now, before we can solve, the last thing we need to do is define the output that we're looking for. And so to do this, we right-click on Solution and then hover over Insert. And a new list of options is going to show up. We're going to be interested in the deformation, and that just measures how much each individual point moves in this object. Now, we have options here, so we can either do total deformation or we can do directional deformation. If you do directional, you also have to specify which direction you're interested in, so we're just going to stick with total. All right, we're also going to be interested in stress. In the simplest form, stress is just force divided by area, but reality is more complex. This is a three-dimensional object, and so there's a lot more going on there. So we're going to use equivalent stress, which is also von Mises stress, and that will take that complex stress state and give it just as a single value. And most importantly, this is the stress that is related to material failure, especially in ductile materials like metal. And so the equivalent stress is best for seeing if a part will fail. All right, then finally, we're going to add the stress tool. So once again, we have options, but we're going to choose equivalent stress. And the stress tool, all it does is give us a factor of safety. And the factor of safety is the failure stress, which it gets from the material definition, that divided by the actual stress seen in the solid. And so this is just another way of visualizing how much stress is present in the part, and also seeing if this thing is going to fail. All right, now that everything is set up, we can solve. This is automatically going to create that mesh using just the defaults that ANSYS has stored. It's going to solve, and it's going to calculate all of the output that we requested. We can click on each of our outputs to see contour plots of those values. For deformation, I'll click here, and we can see the side that we were holding is 0 because we're holding it, it can't move. The side that we pulled on is red. It has the maximum deformation anywhere on the part. For stress, if I click on that one, we see a stress concentration right around the hole. Now, this is a well-known phenomenon, and it can be kind of hand-wavy explained that this is happening because the area here is getting smaller, meaning that the stress, which is force divided by area, is going to increase. But it's not uniform because this is not just a simple one-dimensional problem. It is three-dimensional, but this is about what we expect to see. Finally, we have the safety factor, and this is colored in 4 colors. Red regions are anywhere the material would fail. We don't have any of those. Orange means the factor of safety is between 1 and 5. And so we see that on a good part of our part here, and ANSYS shows us that the minimum safety factor is about 1.65. And then green is between 5 and 10. We have plenty of buffer in those regions. And then finally, anywhere that's blue is 10 and above, where there's really no reason to worry about failure. All right, with that, we have the setup for a simple ANSYS simulation. We had our input, we performed the simulation, and we got the outputs we were looking for out of that. Now, what we did there isn't necessarily a highly accurate simulation, but it is a starting point. So in the next few videos, we're going to take a deep dive into each of these 5 pieces and see how they impact the solution. If we're interested in accuracy, we'll look first at the mesh, because the mesh has nothing to do with what's physically happening, and it's all about how ANSYS understands the problem. So for the mesh, we're going to look at something called a mesh convergence study. And this allows us to see how much that mesh actually impacts our solution. Then for the constraints, for the loads, and for the geometry, these are things that come from real life. Right? And so the best thing we can do is just try to increase the realism. And we'll also play around with the material as well, but as far as the simulation goes, we just have to trust that the properties given by this material are realistic. In any case, I hope this video was helpful, and I will catch you next time.